I welcome you all to the afternoon session of the fourth day of this workshop. And now the next speaker is Anusha Bhattacharya, and she will talk about graph discretization of Riemannian manifolds with Ricci bounds.
The central problem in spectral geometry is to understand the eigenvalues and eigenfunctions of the Laplacian, because they capture deep information about the geometry and analysis of a manifold. But if we try to do that directly with any general smooth manifold, it becomes very difficult to explicitly compute these values. And this is where the technique of discretization comes in. So what we do is, if we have a smooth manifold, we try to replace it with some simpler object, like, for example, a graph in our case. And computing like analogs of eigenvalues and eigenfunctions on graphs is much easier because we can use combinatorial and numerical techniques in those. And using those analogs of eigenvalues and eigenfunctions that we get on the graphs, we can sort of retrieve the information about the spectrum of the Laplacian on the smooth manifold itself. So this is a joint work with my supervisor, Dr. Shoma Mehti, and we have targeted a class of Riemannian manifolds with bounded Ricci curvature and other geometry constants that I'll mention later on in the talk. But our primary constraint was bounded Ricci curvatures, and we apply a particular kind of graph discretization on this to approximate the spectrum of the manifolds over this entire class, and all this process is done uniformly over the entire class. Okay, so we start with introducing the discretization that we are going to use here. So we use something called the weighted graphs. Now we fix a Riemannian manifold M and we fix a metric G on that. And then we have two positive real numbers, epsilon and rho. So the function of epsilon is to choose a vertex set on the manifold, and the function of rho is to dictate where do we have the edges. So using this epsilon, we fix a dense set of points on the manifold, and two vertices are connected by an edge if the distance between them is less than rho. Then we call this discretization and epsilon rho discretization of the manifold M. And here I've just shown three examples, like how does this discretization take place. Then, like if we just consider the raw graph, we will not be able to effectively capture the geometry of the manifold. So what we do is we introduce weights on these graphs. So the technique for doing that is we decompose the manifold using the technique of Voronoi decomposition. So Voronoi decomposition is just that we fix the set of vertices and we pick Voronoi cells around them and partition the manifold into that. And the Voronoi cells are picked in such a way that whatever point is closest to the vertex, we add it to the corresponding Voronoi cell. So if we have n number of vertices, and each vertex, suppose I call them as xi's, then the corresponding Voronoi cells are vi's, and they are also of the same number. So in that way, we decompose the manifold, and on each of the vertices, we attach the volume of the corresponding Voronoi cell as the weight, and the edge weights are chosen in such a way that if two vertices are connected by an edge, then we take the vertex weights and multiply them and add some normalization constant. We'll see why this normalization constant is relevant here, and then we assign the edge weights accordingly.
The number of vertices,
sorry?
Is that 10?
Yeah, that is the same as the number of vertices. So I'll just draw it briefly. Suppose we have some sort of a manifold like this, and we have the vertex sets. Then what we do is, suppose we have another random point here. We see with which vertex is this closest to, according to the Riemannian distance. Now suppose this vertex is closest to this. So if this is x1, then this point P, it belongs to V1. In that way, we partition the entire manifold into these Voronoi cells. And at each of these points, we sort of shrink the whole volume and assign it as the weight on the vertex. So in that way, we are assigning the vertex weights, and the edge weights are also like using the vertex weights. We can define the edge weights accordingly. Then this is just an example of a weighted graph. So I'm trying to approximate a torus here. So I have fixed different values of epsilon and rho, and accordingly I'm trying to plot these graphs. And we can see that as the values of epsilon and rho, they get closer to 0, these graphs become finer, and ultimately in this one we can see that we are getting a very good approximation of the manifold. So this is just a pictorial representation of how this graph discretization works. Now, after we are done with discretizing the manifold, the next obvious step is how do we define a Laplacian on this weighted graph? Because we are trying to capture the spectral information and all, so we of course need an analog of the Laplacian. So on manifolds, the Laplacian, we all know it is defined as the divergence of the gradient. And on these weighted graphs, we define these Laplacians in the following way, where we consider the vertex weights and the edge weights, and we take the difference between the values. Like if we are calculating the Laplacian at the point xi, then whichever vertices are connected to this xi, we are taking the difference between the corresponding values. And that is how we define the weighted graph Laplacian. And we'll in fact see that the spectrum of the Laplacian on this graph, that is the weighted graph Laplacian, this in fact approximates the spectrum of the Laplacian of the manifold. Okay, so now I'll state our goal, that is we want to approximate the eigenvalues and eigenfunctions. Oh, sorry. Yeah, sure.
Yeah.
Sorry? No, it's just the, you can in fact consider smooth functions in that, in this case. Yeah, we are using the density concept here. Okay. So our goal is to approximate eigenvalues and eigenfunctions of the Laplace-Beltrami operator using this technique of graph discretization uniformly over a class of manifolds which have the following uniform bounds. So we are considering all compact manifolds without boundary, and the dimension is fixed. And we are fixing the absolute value of the Ricci curvature with this lambda, and then injectivity radius is uniformly bounded below by I naught, and diameter is bounded above by D. And we denote this class by M followed by all these parameters. So on this class, we'll try to approximate the eigenvalues and eigenfunctions of the Laplace-Beltrami uniformly using this technique of graph discretization. And some previous work was done in this area, that is the work by Burago, Ivanov, and Kurulev. So they have proved uniform spectral convergence of a weighted graph Laplacian, which was the same one, to the Laplace-Beltrami operator for a subclass of this class that we are considering, which comprises of uniform bounds on sectional curvature and the same bounds on injectivity radius and diameter. So knowing the sectional curvature is like you are restricting each and every like curvatures in the two planes. But when we are talking about Ricci curvature, it's like we are taking the average of all these curvatures. So the class that we are working in is much larger than the class considered by them. But essentially, their techniques can be generalized to our work if we try to avoid the sectional curvature bounds like wherever they occur with like bounds that we have derived on Ricci curvatures. So then this is the result that we came up with. So if we consider a manifold from this class and an epsilon rho discretization gamma of M, then if we denote the eigenvalues of the Laplace-Beltrami operator and the graph Laplacian by lambda km and lambda k gamma, Here I would like to emphasize that we are using the sign convention of the Laplacians in such a way that our eigenvalues will always be non-negative. So then we'll find a constant which depends on this entire class and just on the indice of eigenvalue, such that we get this following uniform approximation. So here we see that as rho and this ratio of epsilon by rho, they go to 0, then the graph eigenvalues will uniformly converge to the manifold eigenvalues. So this is the expression of the approximation. And then I would like to mention some key concepts that we have used for getting this approximation. So the first one is that of the Rayleigh quotient. So Rayleigh quotient, it provides a measure of the energy of a function relative to the size of the function. And for the Laplacian, like this holds for both the graph and the manifold Laplacian, the Rayleigh quotient is defined as the following ratio. And this is relevant in our work due to the min-max principle. So the min-max principle characterizes all the eigenvalues of the Laplacian. So this is done in the following way, like if we pick k-dimensional subspaces of the L2 space of the manifold or the graph, then we take all the non-zero elements from this LK subspace and we calculate the Rayleigh quotient of them and take the supremum. And then we take all these k-dimensional subspaces and we calculate the infimum. And then we can see that this is in fact equal to the kth eigenvalue. So this holds for both the manifold and the graph eigenvalues. And now, if we want to proceed further with this Rayleigh quotient thing, there are two parts. So the first thing is we will try to calculate an upper bound of the Rayleigh quotient in terms of the, suppose we are taking the Rayleigh quotient of the graph eigenvalue. So we'll try to calculate an upper bound of the Rayleigh quotient in terms of the manifold eigenvalue and do some sort of comparison, and also vice versa happens. So the first thing is we need to find a way of moving from the graphs to the manifolds. And manifolds to graphs, obviously. And before we do that, we need another thing, that is, if we are trying to find a bound of this Rayleigh quotient, then obviously like we have norms occurring in the numerator and denominator, and these are our L2 norms. So L2 norms means we need to do some sort of integration. And since these bounds should be uniform over the entire class, and integration on manifolds obviously involve Jacobian of the exponential map and stuff like that. So we also need a uniform bound on the Jacobian determinant of the exponential map. And that is what we do here. So we derive this Jacobian estimate by using Anderson's pre-compactness theorem, which basically says that this class is pre-compact in the C1 alpha topology. And from there, we get that the metric quotients Gij and their derivatives are also uniformly bounded. Then using this, we can derive that the derivative of the Jacobian determinant of the exponential map, the absolute value of it, also has a uniform upper bound in this entire class. And we work with small balls when we are doing this Rayleigh quotient and stuff. So there is some approximation on that. And finally, using this upper bound, we apply the mean value theorem and we get a uniform estimate on the Jacobian determinant. So this was the first step in handling the integrals in the Rayleigh quotient. And now comes the second step, where I was talking about finding a bridge between the continuous and the discrete, that is from manifolds to graphs and from graphs to manifolds. So how do we go from manifolds to graphs? So suppose if we have a function on this manifold, so we work with L2 functions here. Then we can define a discretization map that takes this L2 function to a discrete function on the graph vertices. And it is defined as follows, where this P takes the average of F over these Voronoi balls or Voronoi regions along each vertex. So this is how we define the discretization map. And this definition is relevant in our context because if we take any function and its discretization, then the Laplacian on the weighted graph in fact approximates the Laplace-Beltrami operator. And this is why the definition that, the way this graph Laplacian has been defined is relevant in our scenario, because we in fact get this very good approximation, because on the left hand side we have the graph Laplacian and the discretized map, and as these edges they go to 0, these eventually converge to the Laplace-Beltrami operator on the manifold. So this was the motivation behind defining the graph Laplacian in such a way. So now we move on to the other direction, that is from graphs to manifolds. So how do we go from graphs to manifolds? In graphs, we have discrete functions, right? So on manifolds, we need to interpolate them in such a way so that like getting Lipschitz functions are enough in our case. And for doing that, we first of all introduce this notion of a kernel, which acts as a bump functions over small neighborhoods of a point. And this kernel is defined using this psi map, which is normalized to integrate to 1. So this psi is in fact a smooth map, which has this non-zero values from 0 to 1, and rest of the portions it is 0, like in the positive real part. And then we can use it to define the kernel. And using this kernel, we get this associated integral operator, which takes maps from the L2 space of the manifold to Lipschitz functions. And like it is defined by taking the weighted averages using the kernel. And finally, we have this interpolation map. So this interpolation map takes discrete functions from the graph, converts it into stepwise continuous functions on the manifold, and then applies the associated integral operator to get Lipschitz functions on the manifold. So this is how we move from the graph to the manifold. So we have these both bridges ready for us, and also we have that Jacobian estimate for evaluating the integrals. So we finally are ready to see how are we sketching the proof. So for the proof, we use this concept of the average dispersion. So given any manifold, we can define this average dispersion from the L2 space of the manifold to the real line. And this basically calculates how much the functions oscillate in a small neighborhood around it. And the neighborhood is determined by this radius r. So this average dispersion is used to derive an upper bound for the error between a function and its discretization on the graph. So like if our average dispersion is small, then our errors will also be small. So this is in some sense kind of just giving out the error term. And then this average dispersion is also used for bounding the discrete Dirichlet energy. So again, we have this function, we take its discretization, and then we like compute the discrete Dirichlet energy, and we get an upper bound of that using that average dispersion. So we can kind of see that how the Rayleigh quotient thing will gradually come into play, because we have an upper bound on the discrete Dirichlet energy, and from this previous equation, we'll get a lower bound on this norm of f, and then we can take the ratio and get an upper bound on the Rayleigh quotient. So and on the other side, we have bounds for the interpolation map. Again, using the average dispersion, we get this bound. And then we again have this bound on the energy functional, like on the interpolation map. And again, using this average dispersion thing, we get this bound. So the manifold side of the Rayleigh quotient is sorted, and also the graph side. And now we finally calculate the eigenvalue bounds. So we construct a k-dimensional subspace, this L equal to P of W, where W is the span of the first k eigenfunctions of the Laplace-Beltrami operator. Then for any element on this in this subspace, using the bounds that were obtained by the average dispersion, we get an upper bound on this Rayleigh quotient. And the upper bound on this Rayleigh quotient depends on the eigenvalues of M, because these functions were in fact picked from this subspace of the eigenfunctions. And then we finally apply the min-max principle on the Rayleigh quotient, and then we get this approximation on estimate on the eigenvalue of the graph. And we do the same thing on the other side. So here we take the Rayleigh quotient of the manifold Laplace-Beltrami operator, and then we can in fact show that this depends on the graph eigenvalues. And again, applying the min-max principle and doing some manipulations, we get that this graph eigenvalue is bounded below by the following expression, which involves the manifold eigenvalues. So in both of these expressions, the rest of all the terms are uniform. The only thing that we need to get rid of are the manifold eigenvalues to get the uniform approximation. And that is what we do next. So in fact, this paper by Cheng, it shows that for any manifold in this class, we have a uniform positive constant, which gives an upper bound to the kth eigenvalue of the Laplace-Beltrami operator. And this provides a uniform upper bound for eigenvalues across the entire class of manifolds. And then, like finally, if we substitute this bound in the inequalities that we obtained, and if we do some manipulations, then we finally obtain this expression. So in this presentation, like I would just like to summarize what I did is, what we did is we chose this class of manifolds having bounds on this Ricci curvature, and for each of these manifolds, we actually used the technique of graph discretization to approximate the spectrum uniformly over the class of entire manifolds. And these are the references. And yeah, thank you for listening to my talk.
Questions?
Of course, there's numerical lots of applications for this thing, but in terms of like theoretical applications, can you tell me a few things that it relates to?
Okay, for theoretical applications, like in what sense do you mean?
Numerical computation of eigenvalues, but like, I mean, more Riemannian geometry or something.
So, like as far as I know, most of these things are in fact used in applied mathematics contexts. But in theoreticals, maybe like using these techniques, you can in fact approximate eigenvalues for Hodge Laplacians and things like that as well. Yeah, like this was like we were just working on the zero forms, but you can take it to one forms and in higher forms also. So this is something that I can like think about.
Like it's degree matrix minus adjacency matrix.
Yeah.
But here it was different, right? I didn't understand.
Actually, what you have seen is that of the unweighted graph. So for weighted case, the expression that I showed, like you can reduce it to that
Okay.
degree and adjacency form,
Okay.
but that will involve some weighted coefficients as well.
Okay.
But in our case, like this was the best, I
So,
mean, expression.
Like if I take weight to be 1, then can I get all that?
It depends. Like for particular manifolds, if you get the weights to be 1, then yeah, of course, if you take the weights to be 1, it will reduce to that expression.
Okay.
Yeah.
Further questions?
So, so, so in here you have a sequence of graphs which converge to the closed manifold in the Gromov-Hausdorff sense. So is it possible to define the Laplacian for a much wider class of spaces if they have a set of graphs which converge to it in the Gromov-Hausdorff sense?
Sorry, so can you elaborate your question a little bit? Like,
Okay, from what I got, if I'm not mistaken, the gist of your presentation is to show that you can get a Laplacian of a closed manifold if you from the Laplacians of a sequence of graphs,
Yeah,
graphs which converge to it in the Gromov-Hausdorff sense. So supposing if you have any other space, not necessarily a closed Riemannian manifold to which there's a sequence of graphs that converges to it. So is it possible to define some sort of a Laplacian there too?
okay. So you are talking about spaces other than Riemannian manifolds. Okay. So In metric structures, you can do that. Like, in fact, not just for Laplace-Beltrami operator, these things work for other stuff like row Laplacians as well.
Yeah.
Yeah. So,
If there are no further questions, let's thank the speaker again.